In this session, we'll examine the electrical power behind the precision, the energy systems that drive the Hugo Robotic Assisted Surgery platform. While motion and vision define what we see, energy defines what the instruments can do: cut, coagulate, and seal tissue with precision and control. At the center, inside the tower, is a Valleylab FT10 energy platform, paired with Medtronic's LigaSure technology for advanced vessel sealing. These systems integrate seamlessly with Hugo's control tower to deliver consistent, measurable results during surgery. We'll explore how energy moves through the system from generator to instrument tip, and how engineers built layers of monitoring and isolation to keep it safe. You'll see how feedback loops between the generator and robotic instruments regulate energy delivery in milliseconds, protecting tissue integrity. By the end, you'll understand how Hugo transforms raw electrical energy into a precisely tuned surgical instrument. Power, intelligence, and safety fuse in one architecture. Hugo's energy architecture acts like a vascular system for electricity, distributing, regulating, and protecting power across every instrument. The Valleylab FT10 generator forms the core, providing multiple modes for cutting, coagulation, and vessel sealing. It connects through the control tower to the robotic arm instruments using shielded cables and standardized connectors. Within this chain, isolation transformers, grounding checks, and current limit circuits prevent stray voltage or patient risk. The tower's embedded controllers constantly monitor parameters such as voltage, impedance, and activation time, feeding data back to the console for display. Whether the surgeon activates a monopolar scissor or a LigaSure sealer, the software ensures energy remains within calibrated thresholds. If any irregularity, like abnormal impedance or disconnected electrode, is detected, the system halts output instantly. This multi-layered design turns raw power into a governed, intelligent resource, responsive, yet inherently safe. The Valleylab FT10 generator represents the evolution of surgical energy delivery. Designed for both manual and robotic use, it houses independent processors that monitor voltage and current thousands of times per second. Adaptive tissue technology automatically adjusts output as tissue impedance changes, preventing over or under coagulation. When linked to Hugo's control tower, the FT10 exchanges real-time status updates, activation mode, power level, and instrument recognition. The unit's efficiency reduces thermal load, maintaining a cool, stable operation even during extended cases. A color touchscreen allows configuration or service checks, while firmware integration ensures that the robotic console displays generator status without manual input. Together, these elements make the FT10 not just a power source, but a data-driven collaborator, quietly balancing physics and precision in every pulse of energy. LigaSure technology revolutionized electrosurgical sealing by combining energy and pressure under precise control. It works through bipolar jaws that grasp tissue while the generator modulates current flow. Sensors measure tissue impedance continuously, allowing the FT10 to adjust power and duration in milliseconds. The result is a uniform seal, strong enough to withstand 3 times normal vessel pressure with minimal collateral heat. In Hugo, this functionality integrates seamlessly into robotic workflows. The surgeon's console triggers LigaSure activation, and the tower manages feedback between the instrument and generator. Audible tones and on-screen prompts confirm completion, ensuring clarity in the operating room. Beyond safety, the closed-loop control reduces guesswork. The robot, the generator, and the human all agree when a perfect seal is formed. It's a partnership of mechanics and intelligence working at a cellular level. Once energy leaves the generator, precision routing keeps it safe and efficient. Power travels through the tower's distribution board before branching toward the robotic arm cards. Each line is shielded to reduce electromagnetic interference that could distort imaging or data communication. Embedded current sensors monitor the flow continuously, confirming the energy returns through the correct path. The patient return electrode or bipolar circuit without leakage. Optical isolators divide the high voltage and control domains, ensuring that no stray current can reach sensitive electronics or operators. Feedback loops within the tower compare commanded and actual output values in real time, automatically compensating for resistance or cable loss. This intelligent routing turns electricity from a simple current into a managed signal, stable, verifiable, and harmonized with the robot's every move. Safety within the Hugo's energy system is built like concentric shields, each layer catching what the previous one might miss. Isolation barriers separate the generator's high voltage sections from the patient interface and from the robot's digital controllers. Before activation, the tower performs impedance and return electrode checks to confirm a secure circuit. If an open circuit, the ground fault, or abnormal impedance is detected, the watchdog processors cut power instantly and alert the console. Redundant microcontrollers cross-check each other's readings, eliminating single point failure risk. Every component complies with IEC 60601 and IEC 60601-2-2 standards for electrical surgical safety, including leakage current and insulation thresholds. This architecture ensures that while the system manipulates high energy levels, the patient remains electrically isolated and the surgeon remains in control at all times. Communication is intelligence that makes energy delivery precise. Each robotic instrument includes a small chip containing its identification data, type, energy mode compatibility, and usage limits. When connected, the generator reads this data instantly and configures its output accordingly. During operation, the system tracks activation time, delivered energy, and impedance trends, sending the data back to the control tower for logging. This bidirectional communication prevents errors like using the wrong mode or exceeding cycle counts. Maintenance teams can later review the log for predictive servicing or training analysis. The concept mirrors modern smart device ecosystems, instruments that know themselves, systems that listen, and a generator that responds with precision and restraint. The integration of energy systems with the vision and control tower turns Hugo into a single coordinated platform rather than a collection of devices. The tower's processor synchronizes activation signals with imaging and instrument motion data. When the surgeon presses a pedal or finger switch, energy delivery aligns exactly with visual feedback on screen. Shared communication protocols minimize latency, allowing instantaneous energy modulation visible in real time. Generator status and error messages appear directly on the surgeon's console, removing the need to glance at separate units. This synchronization reduces cognitive load and helps maintain flow during complex tasks like vessel sealing or dissection. By merging energy with vision and motion, the tower ensures that every system pulse corresponds perfectly with what the surgeon sees and feels. A unified choreography of technology and touch. Keeping energy systems reliable requires disciplined maintenance. Before each deployment, technicians perform safety tests to verify that leakage, current, insulation, and grounding meets medical standards. Calibration involves connecting known reference loads and confirming the output voltage and current remain within tolerance. During boot up, the FT10 runs self-diagnostics, checking temperature, sensor accuracy, and internal fuses before enabling output. Service ports on the tower allow firmware updates and data export for traceability. Predictive maintenance software analyzes usage cycles and activation counts to schedule service before any issue arises. Together, these practices and ensure consistency and longevity, because in electrosurgery, reliability isn't optional. It's a foundation of safety and precision. So, what's the future trends in robotic energy systems? The next evolution of robotic energy systems is intelligence. Machines that not only deliver power, but also understand tissue. Future platforms will integrate AI algorithms that read tissue impedance curves in real time and modulate energy accordingly, creating perfect seals with minimal collateral damage. Generators may consolidate multiple modalities, COT, coag, ultrasonic, and sealing into one adaptive source. Wireless or inductive energy transfer could simplify the OR floor by removing fake cable bundles, enhancing mobility and safety. Data analytics will help tailor energy profiles to each surgeon's styles, refining efficiency and outcomes over time. In essence, the future points towards self-learning systems, energy platforms that sense, decide, and adapt, transforming electrosurgery from reactive control into predictive precision.